By 2007, Google's infrastructure was approaching a breaking point. Massive C++ codebases were swelling, and the data moving through their servers was growing exponentially. At the same time, processor manufacturers hit a physical wall. CPU clock speeds stalled out, so chip makers began adding multiple cores to single processors. But unfortunately, legacy programming languages were designed strictly for single-core execution. To compile these massive codebases, frustrated engineers were forced to wait hours as build systems choked on linear, sluggish processes. Deployed software suffered an equally severe bottleneck. Network architectures relied on assigning a heavy, dedicated operating system thread to every incoming web request. Under massive cloud network loads, servers simply ran out of memory before running out of processing power. Robert Griesemer, Rob Pike, and Ken Thompson engineered Go to solve these specific cloud-scale bottlenecks. This Google Trends chart tracking global search interest illustrates the result of that engineering focus. Notice the distinct inflection point right around 2012. From that moment, the trend line for Golang begins a massive, uninterrupted climb, parallel to the explosion of cloud computing. Go was designed to do less at the language level in order to bypass the compilation and memory limits that crippled C++ and Java. This design allowed for faster iteration and more stable deployment across massive server fleets. At its core, Go is a statically typed and compiled language. It borrows heavily from the familiar syntax of C, but it is stripped down and rebuilt specifically for modern network processing. The creators applied a strict philosophy of simplicity by omission. They aggressively removed traditional language complexities that slowed down developers. Go completely eliminates implicit number conversions, forcing programmers to be deliberate about data types. They also removed pointer arithmetic. In C, allowing developers to mathematically calculate memory addresses often leads to unsafe, fatal crashes. Go eliminates this practice, maintaining execution speed while simultaneously closing off a massive vector for human error. To further protect the system, Go includes automatic garbage collection to clear out unused data, and it enforces mandatory array bounds checking. These built-in safety nets actively prevent memory leaks and buffer overflows that typically bring down long-running network servers. At the compiler level, Go enforces a strict, highly opinionated package and dependency management system. If you import a package and do not use it, the compiler refuses to run. This guarantees tight code and exceptionally fast iterative build times. By stripping away esoteric language features and blocking unsafe memory practices, Go actively reduces the cognitive load on the programmer. It trades theoretical purity for efficient, highly reliable software development at an enterprise scale. In a traditional concurrency model, every concurrent task is assigned to an operating system thread. Each of these OS threads consumes over a megabyte of memory. Scale up to 1 million requests and your server crashes from memory exhaustion. Go bypasses this hard limit using a construct called goroutines. These are lightweight green threads. Managed entirely by the Go runtime, they start at 2 kilobytes each. The multiplexer dynamically slots hundreds of thousands of goroutines across a few heavy OS threads. If one blocks, it instantly swaps in another. The practical performance benefits of this model are immediate. Servers built with Go execute with near-instant startup times, and they can handle millions of concurrent connections simultaneously on cheaper, standard-issue hardware. Goroutines restructure the economics of back-end infrastructure. They grant developers the ability to execute parallel processing without the overhead of traditional thread management. To manage communication between concurrent routines, Go relies on a philosophy from Tony Hoare. Don't communicate by sharing memory, share memory by communicating. Traditional programming allows multiple threads to access the same block of shared memory. To prevent overwriting, engineers write complex locks and mutexes. Get it wrong, and you cause system deadlocks. Go uses channels, built-in conduits where goroutines safely pass data. Unbuffered channels block execution until the receiver is ready. Buffered channels have a fixed queue, allowing the sender to drop off multiple messages and continue working. Channels beautifully abstract away complex synchronization. But for engineers migrating to Go, this abstraction often creates a false sense of security. There's a persistent misconception that channels eliminate concurrency errors. The reality is that channel-related bugs still represent the majority of blocking issues in Go applications. Consider a real-world case study discovered by researchers in the Kubernetes codebase, a severe mixed deadlock inside a function called Status Manager. The architectural flaw lies in the struct setup. The developers mixed a modern Go unbuffered channel with a traditional mutex shared memory lock. Thread G3 acquires the mutex lock, then attempts to send data into an unbuffered channel. With no receiver, G3 halts, holding the lock. Simultaneously, thread G1 attempts to receive data, but needs that exact same lock. Both are permanently blocked. The result is catastrophic. Both routines enter a total deadlock. Neither will ever terminate, and the system begins quietly leaking resources. Go offers immense processing power, but it demands strict architectural discipline. Engineers cannot blindly mix the channel paradigm with shared memory locks without a deep mechanical understanding of the runtime scheduler. The combination of Go routine multiplexing and a low memory footprint allows developers to build and scale decoupled microservices efficiently. Instead of wrestling with a single monolithic application, massive engineering divisions can scale. Independent teams write, manage, and deploy distinct, fast-compiling services that communicate seamlessly across the network. Twitch uses Go's low-latency garbage collection to process and route live video and chat messages to millions of users simultaneously. Uber relies on Go to execute real-time geofence querying and to run the heavy resource scheduling engines that coordinate millions of drivers and riders globally. Through sheer utility, Go has become a foundational language of cloud computing, natively powering over 75% of the projects in the Cloud Native Computing Foundation ecosystem. This chart from a 2020 developer survey lists the most loved programming languages in the industry. Despite its strict compiler rules and missing features, Go commands a 62.3% positive rating among working engineers. And this visual, tracking the top-paying technologies from that same year, places Go near the top with an average salary of $74,000, proving its market value to the enterprise. Go succeeded specifically because it rejected feature bloat. Its creators prioritized operational pragmatism, fast compilation, and unyielding concurrency performance over theoretical elegance. Go remains defined by operational pragmatism. It was built to do less at the syntax level, so it could enable more at the system level.